Welcome to the video cast on Chapter 14, Kinetics. Please have some paper and a pencil out. Pause the video now and make sure you've got those things out before you start the actual video cast. Having a copy of the reactions page out is helpful as well. Chapter 14 is divided into two parts. First of all, determining rates and what causes the speed of a reaction to be what it is. And second of all, to determine the mechanism or the makeup of the chemical reaction. We're going to take a number of pages of notes, so make sure you have a bunch of paper out. Pause the video as you need to along the way. The rate or the speed of a chemical reaction is determined by four factors. First of all, the state of matter, whether there's a lot of surface area, a little surface area, whether it's hot, cold, things like that. The concentration of the substance, the temperature of the substances or substance, and whether there's a catalyst present. We're going to take a look at rate and concentration first. Rate and concentration first. We don't really talk about states of matter very much, just that if it's spread out more, it's going to react faster. So, the more surface area there is, the more reaction there is. We're going to take a look at rate and concentration first. First of all, we describe rate mathematically as the change in concentration divided by the change in time. The change in concentration of the reactant divided by the change in time. Triangle means change. These brackets right here, remember, mean concentration of in terms of molarity, and T here stands for time, whether it be minutes, seconds, hours, days, years, centuries. When we talk about rate, we mostly talk about what's called the instantaneous rate at the start of the reaction. The instantaneous rate. At that instant, how is it changing? And usually we talk about it at the start of a chemical reaction. We look at this relationship in an equation form. We look at this relationship in an equation form. In this equation form relating concentration and rate of a reaction, is told to us by the stoichiometry of the equation. So, for example, when two HIs disappear, one H2 appears. When two HIs disappear, one H2 appear. So in 10 seconds, if 1 mole of HI disappears, how much I2 appears? You can see here that if 1 disappears, how much I2 appears. You can see there's a 2-to-1 ratio in the equation. So if 1 disappears, 1/2 would appear. Half as much would appear on the right-hand side. Okay, next, we're going to take a look a little bit more after this appearing and disappearing. We're going to look at the rate law. Now, the rate law is the equation that describes how the reaction changes with respect to concentration. And it always takes this form, where the word rate is written, and it is equal to some constant represented by the letter K, times the reactant to some power, times another reactant to some power, times a third reactant to some power. And the reactants are always put in brackets, meaning concentration. The rate is always in units of molarity per some unit time, or concentration per some units time. The rate constant units are dependent upon the reactants, the number of reactants and their exponents, and of course the unit of time that you're using as well. The M and the N are called the order of reactants. The orders are the exponents that are used and must be experimentally determined. So for reactant 1, it's to the order M. For reactant 2, it's to the order N. The M and the N are the powers, and the special name given to them in a rate law is the order of reactant. The reactant 1 and reactant 2 are put in brackets, like I said before, and that tells you the concentration of those reactants. And if there's more of them, then you'd have reactant 3, reactant 4, all to those powers. those powers, once again, are called the orders of reaction. And those are the things that they usually want you to experimentally determine. If you take the orders m and n and any other ones and add them together, you'll get what's called the overall order of the reaction. You can only determine the rate law experimentally. You can only determine this entire equation by doing experiments and then doing some mathematics to determine how the concentration of those rates affect it. So you can only determine it experimentally, and if you don't determine it experimentally, you'll have to guess. We're going to come back to that in just a second. We're going to do some problems that involve that from old released AP exams, but right now we're going to take a look at, we're going to come back to this in just a second, right here, this rate law stuff. But right now we're going to take a look at what happens if the concentration, or what if we want to look at the concentration versus time. Well, if it's a first order rate law, the first order rate expression law takes on the form rate equals constant k times a to the first power. This rate expression or rate law can undergo some mathematics called integration. When we integrate it, we get the form of the equation natural log of a of some time minus the natural log of a naught is equal to negative k times t. Notice that it's natural log of a to some small letter t, that's the concentration at some time, and natural log of a with a little 0. That 0 is actually an O, meaning original. This is for the first order rate equation, first order, and that's when the concentration is to the first power. Notice they give you the first order rate equation on the yellow periodic table, and it's towards the bottom, and it shows you that the equation that I just wrote up there is in the same exact format as down there. You don't have to memorize the equation. Now, if you do a little bit of math to this equation and you take the natural log of a original and stick it on the other side of the equation, now you've created an equation in the form of y equals mx plus b, which of course is a straight line equation. And you could take and you could graph this, putting the natural log of a on the vertical axis and time on the horizontal or the x-axis. Now, I drew two lines on here. One you can't see real well, one with red dots. Which one is the actual line that should be drawn? Notice it's a straight line equation, but which one fits? Well, the one that is written in pen has a positive slope. The one that's written in red has a negative slope. And so it's the negative slopes line that you would want to put for a first order rate law expression. First orders always have a straight line with a negative slope when you graph the natural log of concentration versus time. And you can notice that the y-intercept is the natural log of a original. So the original concentration can be determined by looking at where the line intersects or intercepts the y or vertical axis. For a second order reaction, rate is equal to k times the concentration of a to the second power. Rate is equal to the concentration to the second power. And if you perform integration on this, now you end up with the equation 1 over AT minus 1 over A naught is equal to KT. This integrated rate law equation is also given to you on the crappy periodic table, and I'll show you where that is in just a second. But if you take a look at this and take the A original to the other side of the equation, you now also get the equation in the form of a y equals mx plus b line. You'll notice that the y-axis then is 1 over concentration. The y-intercept is 1 over the original concentration. And the horizontal axis is time. So you can see 1 over concentration is the vertical axis. Time is the horizontal axis. And this time you're already ready for it. Notice that you'll get a straight line with a positive slope because it doesn't have a negative sign in here like the first one did. So notice this equation is also given to you on the yellow periodic table. It's right below the first order. It's the second one listed, so you know it's the second order integrated rate law equation. And you can see it's in the same format that I gave you before. I did a little bit of math with it. And you've got a good place where you can go and look, and you can find the first and second order integrated rate law equations. Both of those are given on the periodic table in that format, the one that I circled right here. Notice that it's not in the form of the line. You have to take and move the original concentration to the other side to get into that format. Well, what happens when you use up half of the amount of stuff? Then you achieve what's called the half-life of the equation. And for a first-order equation, if you're looking at the half-life, you get to half of the original amount. And notice I put a little 1/2 times the O there. 1/2 times O is half the original. And there's the original amount. And if we do a little bit of mathematics here, we can take these natural logs and we can put them together. So then I remove the brackets to make it a little easier to see. Natural log of 1/2 of A divided by the concentration original, that's just that A, is equal to negative KT, and I put a 1/2 below the T so you know that it's half the time. Now you notice that the A's cancel with each other, so you end up with the natural log of 1/2 is equal to negative KT. Switching the K and the negative sign to the other side and taking the natural log of negative 1/2, you end up with T1/2 equaling 0.693 divided by K, because that's the natural log of negative 1/2. So this half-life equation, T1/2 is equal to 0.693 divided by K, this half-life equation is not given on the periodic table. So you either have to memorize it or you have to be able to derive it. Note that it's independent of the original concentration. Notice that A with the little 0 or AO is not in the half-life equation. First order is unique in that way. A second or a third or a 0th order integrated rate law would not have that. It would be dependent on how much you started with. A first order reaction is independent of that original amount. So since half-life of a first order reaction is independent of the amount of the original concentration, we'll look now at a second order half-life equation. And you'll see that that is dependent or depends on the original concentration. Now the same mathematics applies here, that you could derive this. This is not given on the yellow periodic table, but the important thing to notice is that it does depend on the original amount of stuff that you started with, whereas a first order is independent of the amount of stuff or amount original concentration that you have. So there's the first order and second order half-life equations that can be used. And let's go on to talk about what we actually need to start a reaction. This is called the activation energy. It's the amount of energy needed to initiate a chemical reaction. The amount of energy needed to initiate the chemical reaction could be a spark, it could be a flame, it could be dropping something, it could be banging something, it could be an explosion, or could be as simple as just a spark. If we diagram this on a potential energy diagram, where potential energy is on the vertical axis and reaction pathway is on the horizontal axis, you can see that we can show graphically how starting at a certain amount of potential energy and then following the graph along, we can see that we reach a high point of a graph where we'll actually reach the activation energy. And then when we reach the end of the reaction, it levels out again. This tip top is called the E sub A, or the activation energy, or the activated complex of the reaction. Activated complex of the reaction. And if we find the height from the beginning to the top of that activated complex, that's known as the energy of activation, or E sub A. If we find the height change from the beginning to the very end, we can now find, as long as it's at constant pressure, the enthalpy of the reaction, or the change in heat of the reaction. And of course, since we end up higher than what we started with, you can see that it is a positive enthalpy, or it would be known as a endothermic reaction. So we can use this reaction pathway to help determine not only the enthalpy of a reaction, but also the activation energy. But the question still arises, how do you calculate the activation energy? Well, if you look at temperature and an equation devised by Svante Arrhenius a number of years ago, you can actually use it to help determine the activation energy. This bomber of an equation right here can help you solve for E sub A. As long as you know the rate constant, K, you can find E sub A in kilojoules using the universal gas constant, R, times 1 over the Kelvin temperature plus the natural log of something called the frequency factor. That's the letter A. So what does each one of these letters represent? First of all, K is the rate constant. K is the rate constant. And you'll notice that this entire equation takes on the form y equals mx plus b, just like we had some other equations do that, where y, or the vertical axis, would be the natural log of the rate constant. I apologize. X, or the horizontal axis, would be 1 over the Kelvin temperature. That would be the horizontal axis. Once again, y was the natural log of K, and X, or the horizontal axis, was 1 over the Kelvin temperature. And the slope of the line is the activation energy divided by the gas constant, which is 0.00831. Notice it's in kilojoules per mole. That's why it's 0.00831. And the y-intercept is what's known as the frequency factor. Frequency factor tells us something about the frequency, or number of collisions that some of the particles would undergo in the initiation of the reaction. Excuse me. For the graph, then, you'd graph the natural log of the rate constant on the vertical axis, and you'd graph 1 over the temperature on the horizontal axis, and then I have some questions written down here about it. What kind of line would it be, and what does the slope tell us? First of all, what kind of line would it be? Well, you've gotten used to this from the past couple of them. Notice it would be a straight line, y equals mx plus b, but it would have a negative slope. So once again, we'd end up with a line that goes up and to the left when looking at the graph. Straight line with a negative slope. And what does the slope tell us? Well, the slope of the line, once again, is used to determine the activation energy for the reaction. So you can determine the activation energy for a reaction by knowing the rate constant and temperature. And usually what you do is you take a series of reactions and you find the rate constants for those reactions and perform them at various different temperatures, and then make that graph to solve for the activation energy. There hasn't been a question actually solving this equation in many, many years, but there have been questions asking about the graph and the slope of the graph and how you could use it to find the activation energy. Here's where this equation is on the yellow periodic table. You can see that the equation is given in exactly the same form that I give it to you, in the y equals mx plus b format. And so you know where the horizontal and the vertical axis are, and where to find activation energy by looking on the yellow periodic table. Okay, moving along, let's talk about mechanisms of reaction. Mechanisms of reactions now, of course, tell us the step-by-step process in which a reaction is going to take place. First of all, here is the 3 different types. If one thing just reacts and produces something, it's called a unimolecular process. If 2 things react, it's called a bimolecular process. If 3 things react, it's called a termolecular process. And of course, the uni and bimolecular processes are very probable because they could happen, but a termolecular process is not very probable at all because 3 things colliding with the right orientation is very unlikely. We can use these types of processes to help drive or determine what the rate law would be. Because if you know what the process that determines the rate expression is, you can use it to determine what the exponents of the rate law are. And this is the 10th edition of Brown-Lemay. And if you scroll in here, on table 14.3, you can see that if it's a unimolecular process, and that is the rate determining process or step of the reaction, then it's going to be to the first power. If it's bimolecular, it's going to be to the second, or each portion is going to be to the first power. And then there's the termomolecular processes, which are not very probable. So you can see you can use the elementary reaction steps that are rate determining to help determine the rate law. Or conversely, by knowing the rate law, you can determine the elementary steps. They go back and forth. So when you know the rate law expression, it can help determine the mechanism of the reaction. So rate is equal to some constant K times A. It's a unimolecular step, and you know that the slow step of the reaction then is A goes to some products, and it would be defined as the slow or rate determining step. They have to tell you it's slow, or you have to make an educated guess that this is the slow step, this is the rate determining, this is what the rate law would look like. Here's one that has A and B in it, and you can see that A plus B would be the slow step, therefore the rate law exponents would match the coefficients in front of A and B. A and B have 1s in front of them, and the exponents for A and B are both 1 as well. 1 there for B, 1 there for A, 1 there for that A as well. Page 602 at the top, once again, intensive addition of Brown-Lemay-Burston. You can see in this graph, you can see that for the different types of processes, you can get those particular rate laws. So if you had a rate law of rate equals A times B, you'd know that A plus B goes to products must be the rate determining step because the exponents match the coefficients of that rate expression. So let's answer a couple of questions using mechanisms. Here's a mechanism for a reaction. N2O yields N2 plus O, slow step. N2 plus O goes to N2 plus O2, fast step. The slow step, of course, is the rate determining step. And so the first step is going to be the one that determines what the rate law is. We don't even have to look at the fast step for that. But we're going to ask a couple of questions about this first and see if we can answer them by using these two steps. This is a really similar question that happened in 2010, and we'll come back to it in just a second. We'll actually go to 2010 in just a second. First of all, by knowing the two steps, you can write the overall rate, the overall reaction. And to do that, just take the things that are on the left side and put them all together, and then take the things on the right side and put them all together. So in this case, you'd take two of the N2s, two of the N2Os and the O, and then you'd take the two N2s and write them on the right side, and an O and an O2. And you'd notice that you'd want to cancel out the things that are the same on both sides, and the O's cancel out. Now there's your overall reaction. 2 N2O yields 2 N2 plus O2. That would be the overall reaction by combining those two. Now, part 2, question 2, please write the rate law for the overall reaction. And the rate law, of course, is governed by the slow step. And the slow step has only N2O as a reactant. So rate is equal to some constant K times N2O to the first power, because there's a 1 in front of it in the slow step. If it is the slow step, you can take the coefficient and write it as the exponent. But it has to be the coefficient from the slow step. You can't just look at any old reaction. It has to be the slow step of the mechanism of the reaction to make it be the actual exponent for the rate expression or the rate law. Write the rate laws for step 1 and step 2. Well, for step 1, it would be the rate determining step, so K times N2O to the first power. And for step 2, rate would be equal to some constant K times N2O times O, both to the first power. But of course, step 2 is not rate determining, so really we don't really care about step 2's rate expression. Rate law, or step 1 is the one that determines the actual rate of the reaction. Rate step 2, we just are able to write it because it's available. Please identify, question 3, identify any intermediates and identify any catalysts. So any intermediates Well, you can see that O is produced in the first step of the reaction, and then you can also see that O is consumed in the second step of the reaction. This is the definition of an intermediate, because it's created in the middle or in between two steps in a reaction. Those things cancel out with each other. So we have identified an intermediate O. Are there any catalysts in this? Well, a catalyst is something that is present at the beginning of the reaction and also present at the end. And there is nothing that's present exactly the same at the beginning and at the end of the reaction. So there are no catalysts in this particular example problem. So what is a catalyst? Well, of course, all chemists know that a catalyst is a list of your cows and bulls. But that's just a chemistry joke. So catalyst is really one of two things. Either a heterogeneous catalyst, which means that it is of a different phase than the actual reaction, or a homogeneous catalyst, meaning it's the same phase of the reaction. On page 609, we can see that a catalyst actually offers an alternative pathway, offering a lower activation energy for the reaction to occur. It lowers the activation energy, offering an alternative pathway for the reaction to occur. And we can see here on this diagram, potential energy on the vertical axis, reaction pathway on the horizontal. You can see that the red diagram shows the uncatalyzed reaction. The blue diagram shows a catalyzed reaction with two separate elementary steps. Which one's rate determining? Well, of course, the taller one is the rate determining step, because that one takes more energy to occur. You can see that there's an intermediate in the middle, and you can see that there's two steps in that catalyzed reaction. But of course, the overall catalyzed reaction takes less energy. Well, let's take a look at some of the released advanced placement examinations, and let's go over a couple of the problems. And let's go back to the very original, one of the first questions we had. This is from the 2008 Form B, question 2. Write that down. Write that down in your paper so then you can go back and take a look at this. And in this one, it says, for the gas phase reaction represented above, the following experimental data were obtained. You can see that it's A plus B yields C plus D. And it gives us a bunch of experimental data, tells us the initial concentrations of A and B, and the initial reaction rate for 1, 2, and 3, but not for 4. The question says, determine the order of the reaction with respect to A. Justify your answer. So let's take a look at how a couple of the concentrations change and how those affect the initial rate of the reaction. You can see from reaction 2 to 3 that the concentration of B does not change hardly at all. And remember, this is an experiment, so 1/1000th of a difference in molarity is not really going to make a whole lot of difference. Remember, it's pretty difficult to get to 1/1000th of anything in the lab. And you can see that the initial rate of the reaction doesn't change hardly at all as well, from 1.08 to 1.07. Okay, so we didn't change B, and the reaction rate did not change. But we changed A. You'll notice A went from 0.034 to 0.136. We quadrupled it. And when we quadrupled the concentration, the reaction rate didn't change at all. That means that A must not affect the initial rate of reaction at all. And what power do we give to something that does not affect the initial rate of a reaction? Well, it might be a surprise, but it is called a zero-order reaction. And so we would write A, concentration of A, to the 0 power. That would be the first part of our rate expression. A to the 0 power, because it does not affect. And anything to the 0 power, of course, is 1, and so it would just be rate is equal to K right now. And let's read what they said. They said between experiments 2 and 3, B stays the same and A is quadrupled, but the initial reaction rate stays the same. This means that the initial reaction rate is not dependent on A, so the reaction is 0 order with respect to A. You can justify it with some mathematics as well, which we'll do with the next reaction, actually. Determine the order of reaction with respect to B. Justify your answers. So now we're going to look at B. We're going to take two reactions there, and we're going to do this mathematically. So we're going to take and compare rate 2 to rate 1. Rate 2 to rate 1. So here's the rate for 2, and here's the rate for 1 you'll notice that it changes. And you'll see that the rates are divided by each other, and that we take the rate expression for each one and write it out as k times a to some power b to some power, k to some power a to some power b to some power. And it's those exponents that we want to know. Of course, we know that a's exponent already is 0, and that'll drop out of the equation here in just a little bit, because anything to the 0 power is 1. And then we plug in the rates. And you can see that the rates from A and B are written in, and then you can see that the concentrations from A and B are written in as well. The K's and the A concentrations will cancel out. You can take and divide the rates, and then you can also divide the concentrations of B and raise them to the y power. X is 0. Remember, that's going to turn out to be just 1, so we cancel that guy. K's will cancel. Do a little dividing. That ends up being 16.2, and the 0.137 and the 0.034 ends up being 4 to the y power, so now you got to guess and check. 4 to what power equals 16? And if you guess 2, you win a prize. So the reaction is second order with respect to B. So if we were to write the rate expression for this overall reaction now, we would write the rate as, well, we're going to write the overall rate expression right now because that's the next question. Rate is equal to some constant K, concentration of A to the 0 power, times the concentration of B to the second power. And of course, the A to the 0 power would cancel out, and that would be taken out of the expression, and that's what they do for the exam question, is rate is equal to K times B squared. Okay, let's take a look at another exam problem. This one is similar, but it has a fun twist to it as well. This one has a little bit longer reaction, and it's from 2003, question 3. Write that down, 2003, question 3. It says, in a study of kinetics, the reaction listed above, the following data were obtained at 298 K. And then there's a bunch of data given below here, and they give you the initial concentrations of 3 different things and the rate of disappearance for those 3 things, which is, of course, the rate. And then they give you 4 experiments. From the data given above, determine the order of reaction for each thing listed below. Show your reasoning. So we're going to start with, let's see, letter A says determine the order of BR minus 1. We'll look at experiments 1 and 2. You'll notice BR is doubled from 1 to 2. And BrO3 stays the same, and H plus stays the same, and you'll notice that the rate goes from 2.5 to 5. So it itself is doubled as well. So when you double the concentration, you double the rate. Now, you can do that mathematically as well, and they plug the numbers in there, comparing rate 2 to rate 1, so putting the 2 numbers on the top, and the reaction or experiment 1 numbers on the bottom. And when you do that, you end up with 2 equaling 2 to some power, so you know that it must be 2 to the first power, so it's first order with respect to BR minus. First order with respect to BR minus. So keep that in mind, that BR minus is to the first power, because we're going to come back and use that in just a second. And then you can see in the second one now, we're going to take BrO3 minus and determine that. We're going to compare experiments 1 and 3. And compare experiments 1 and 3. So you'll see 3 and 1, and that H plus stays the same from 1 to 3. BrO3 is like not doubled, but like halved and added to it. And then experiment experiment 1 to 3 for BR minus stays the same. Stays the same. So you'll also notice that the rate of disappearance, or the rate of the reaction, goes up by taking like half of it and adding it to it. So it looks like the rate goes up by the same amount. But here's the mathematics of it. Compare rate 3 and 1. Put rate 3 on the top, rate 1 on the bottom, just like we did before. Put those rate numbers in there. and then all the numbers of the concentration, and we already know that Br minus is first power, so it's first order, so we put a 1 in there. We see that H plus and Br cancel out, and the K's cancel out. Doing the mathematics, you get 1.5 equal to 1.5, and you have to guess and check, and of course you better guess first power there, because 1.5 will not equal 1.5 if it's not to the first power. So in this case, the exponent for BrO3 is also first order, or first power. Keep those in mind, because now comes the tricky question. The next page actually asks you to determine the order with respect to H plus. And if you look at the data, from the experiment, you'll notice there's no experiment in there where H plus doubles or halves, and the other ones remain the same. And so you simply have to pick 2, and in this case we picked 3 and 4, and plug the numbers in that you have from the other experiments. And so you can see that they compared experiment 4 to experiment 3, and they plugged in the numbers from 4 and 3 for Br minus, BrO3 minus, and H plus. And you can see that the Br minus ends up staying the same, but the BrO3 actually changes, and we kept those numbers in there and raised them to the first power because we knew it was the first order. And when you divide the rates, it ends up equaling 8, and this is equal to 0.015 divided by 0.0075, which is equal to 2. So you end up with 4 equaling, when you do the other division for the H plus, 2 to some power. So guessing and checking, 2 squared is equal to 4, so H plus must be second order. Right, the overall reaction order rate law then, you can see that it would be Br to the first power, BrO3 to the first power, and H2 to the second power. Determine the value of the specific rate constant. Well, now you take the rate law like this, solve it for K, and then plug in numbers from any one of the experiments. And they used experiment 1 right here, put the data in, and notice they also found the units for that. The units ended up being molarity to the -3, seconds to the -1. They love negative exponents on this, and you should start to love them as well. So 1 point for the value of the rate constant, 1 for the units. Okay, let's take a look at a real recent question, 2010, Form B, question 6. This is the one that I referenced before, is going to end up being really similar to a problem we did just a little while ago as an example. But this one starts out with the same types of questions where we have some experimental data. And then this happened in question number 6 of the 2010 exam, so you could not use a calculator here either. So you could mathematically compare it, but you just have to look at how it changes. So you'll notice that from experiment 1 to 2, H2 doubles, Cl stays the same, and the rate doubles. So that means H2 must be to the first power. So when you double one and the rate doubles, the other one stays the same, it's first power. Then it has to find the reaction order with respect to Cl minus. You can see that Cl minus doubles from 2 to 3. I'm sorry, from 3 to 2. From 3 to 2, going up. And H2 stays the same. So since it doubles and the rate doubles, Cl2 must also be first order. So write the overall rate law. Rate is equal to K, H to the first power, Cl to the first power. Write the rate constant. Once again, solve for K. Plug in the values of the rate constant. Don't put the numbers in now because they're only asking for the units. And then solve for the units, and you can see that that one's actually really fun to do. Then on the back side, it becomes a little more fun. Question E says, predict the initial rate of the reaction if the concentration of H2 is such and such and Cl is such and such. So now you have to plug these numbers into the expression, the rate equals K expression, and solve for that rate. And then they give you a mechanism question where step 1 is N2O goes to N2 plus O, and O plus N2 goes to N2 plus O2. Write the balanced equation for the overall reaction. We actually did this one just a little while ago as an example of adding the two together and getting them. Hard to believe it showed up in an AP exam when it was an example problem from the book. And the oxygen atom is an